All right, today we're going to talk about a real superpower in calculus, infinite series. These things are the key to taking functions that are just wildly complicated and turning them into something you can actually work with. It's pretty cool. Let's dive in.
So you learn calculus, and it feels like this incredible machine, right? It can solve almost anything. But what happens when that machine just stalls out? What do you do when you run into a problem that your standard calculus toolkit just can't crack? And believe me, it happens a lot more than you'd think.
Well, meet one of those walls. This is the Gaussian integral, and this thing is huge in probability and statistics. It's basically the engine driving the bell curve. But there's a big problem. You can't solve it. I mean, there is no simple everyday function out there whose derivative is e to the minus x squared. So, are we just stuck?
Not at all. And this right here, this is the big idea. If you can't integrate the function, then just change the function. We're going to swap out that complicated e to the minus x squared for something we absolutely can integrate, a simple polynomial. And that's where our hero comes into the story.
And that hero's name is the Taylor series. A Taylor series is basically a universal translator. It takes a complex function and just rewrites it as an infinitely long but really simple polynomial. We're talking a sum of easy terms like x and x squared and x cubed. And the magic of that is we know exactly how to integrate those.
Okay, so that's enough theory. Let's see this superpower in action. We're going to tackle another classic impossible integral. And this time we're bringing in the sine function.
So here's our mission. Calculate the integral of sine of x divided by x. And yeah, you guessed it, just like the Gaussian function, this one has no simple antiderivative. But with our new series toolkit, we can totally handle this.
And the process for this is actually kind of beautiful. Step 1, we just write down the Taylor series for sine of x, which is a famous one. Step 2, we divide that entire thing by x. And look what happens. Every single term just loses a power of x. That's just algebra. And for step 3, we just integrate this new polynomial one piece at a time using the good old power rule. And since it's an indefinite integral, we got to remember to add our constant of integration, that plus c. And we're done. We just solved an unsolvable problem.
Finding a general solution like that is great. But what if you need an actual concrete number? Well, in this next part, we're going to see how series let us approximate the value of a definite integral.
Okay, here's our new goal. We need to estimate the integral of sine of x squared all the way from x equals 0 to x equals 1. Again, there's no way to integrate sine of x squared directly, so you know the drill. It's time to call in the series.
The process here is just as slick. First, we start with that basic series for sine. Let's just call it sin u. Then we do a simple substitution. Everywhere we see a u, we just pop in an x squared instead. And just like that, bam, we have the series for sine x squared. Now, all that's left is to integrate that polynomial from 0 to 1. So let's start approximating. If we only take the very first term of our integrated series, that's the x cubed over 3, and we evaluate it from 0 to 1, we get 1/3. So that's our first guess. It's a little rough, but it's a start. But hey, we can do better, right? Let's add the second term into the mix. So that integrated second term was x to the 7th over 42. Our approximation now becomes 1/3 minus 1 over 42. You can see how each term we add just fine-tunes the answer, getting us closer and closer to the real value.
And there it is. Just using two terms gives us a pretty good approximation of about 0.31. Think about that. We took a definite integral that's theoretically impossible to solve exactly, and we pulled out a solid numerical answer. That is the practical power of series right there.
But wait, there's more. This whole polynomial superpower thing isn't just for integration. This technique makes a bunch of other messy operations way easier too.
Just take a look at this. How would you even deal with a function like e to the x times cosine of x? I mean, finding its derivative with the product rule is already annoying. But now look at its series representation. It's just one polynomial being multiplied by another one. Hey, we know how to do that.
And the method is exactly what you'd think it is. You just multiply it out term by term, and then you collect all your like terms, you group together the constants, the x terms, the x squared terms, and on and on. We just turned a complicated calculus operation into simple algebra. It's just fantastic.
So let's wrap this up. What are the key takeaways? Well, at their core, Taylor series are a total game changer. They let us crack open these so-called unsolvable integrals by turning them into simple problems. This means we can actually calculate real-world answers for things that seemed impossible.
And as we just saw, this whole toolkit is good for more than just integrals. It simplifies other messy operations too.
And you know, that leaves us with a final thought. We spend so much time in math trying to find the perfect, exact answer. But in the real world of physics, engineering, and data science, everything's based on measurements, which always have a little bit of uncertainty. So in that world, maybe a really, really accurate approximation, the kind we get from series, isn't just good enough. Maybe it's actually the most practical and useful tool we have. Something to think about. Thanks for watching.